The components of motion are the position, the velocity, and the acceleration. And in order to see how they're related to each other, I want us to look at the units, right? How do we measure position? Well, position is measured using units like feet or meters, right? It's some sort of distance. And so, well, it's related to distance. It tells you where you are compared to like some starting point, right? And so that means that you're sort of measuring a distance from start to wherever you are. So this is, for example, meters. I'm going to use the conventional units and that are in physics. So meters, right? Velocity, when you think about maybe real life situations where you've heard of velocity, maybe a car might come to mind. And the units we use are miles per hour. But in physics, right, it would be a different set of units, but it would still be, if you think of miles per hour, miles represents some sort of like distance, right? And this represents time. So in physics, our units would be a distance, which is meters, over some sort of time, seconds. Right? And that's kind of describing how fast something is moving, right? How fast your car is moving, how fast a plane is moving, how fast you can run, right? Meters per second. An acceleration has to do with not how fast you're moving, but how fast you're speeding up or speeding down, right? So if you're already maybe driving your car at 10 miles per hour and you accelerate, you're going to increase that velocity. So your velocity changed. And so we're going to get to the units of this in a second, but I think what will help is if we first relate position to velocity. How are these related, right? Okay, so let's say you have a car, right? And you're at your house. And we'll call your house like base 0, right? This is, if you're at home base, then your position, we'll call it 0, right? So at this moment in time, your car is a position of 0 meters. But then let's say you start easing out of your driveway. And we'll assume that you kind of just take your foot off the brake. I don't know. This is a little difficult because obviously in order to start moving, you have to accelerate. But let's just say at some point you get to move, right? So you have a velocity. And if you have a velocity, are you going to be staying in the same space in your driveway? Or is that going to change? You should end up moving and changing your position to some other place, right? So maybe you're like 10 meters away. If you're 10 meters away, right, there's obviously a change in position. How did that happen? Because there was a velocity. And so that's how position and velocity are related. Velocity is the change of position over the change in time. That is a type of rate of change. And if you're looking at trying to find the velocity at a moment in time, at an instant, then that means you care about an instantaneous rate of change. Trying to write an I and an N at the same time. And therefore, if we know that position and velocity can be related through a rate of change or an instantaneous rate of change, that should tell us that they are related. Through the derivative. Similarly, if we think of acceleration and velocity, right? If your car is moving at 10 meters per second, right? Or maybe let's say 20 meters per second, I don't know. Trying to just pick a different number. Let's say 5 meters per second. That's how fast you're moving. And you hit the gas, right, to speed up. You're going to accelerate. And will you still be moving at 5 meters per second? Or is that going to change? If you're trying to speed up by pressing the gas, your velocity should be changing, right? In this case, it should increase. So at some later point, maybe you're going at 15 meters per second, right? You sped up. Similarly, if you're coming to a red light, you need to hit the brakes. And are you gonna still be moving at 15 meters per second? No, you're gonna slow down because you need to stop, right? And so eventually, the cars are getting worse and worse. Right? If this was your stoplight, then you would be moving at 0 meters per second, not at all, because you had to slow down and stop. So again, like pressing the gas or pressing the brake changes your velocity. That's what acceleration is a change in velocity over a change in time. So again, this has to do with a rate of change. And if you're looking at one moment, then you're looking at an instantaneous rate of change, which means you can take a derivative. Now the units for that, right, if we're looking at the rate of change of velocity, change in velocity over change in time, means we're going to take the units of velocity, right, velocity over change in time. That's going to get you meters per second squared. And so what I want you to try and do is think about if I gave you some position function, right? Let's say I said s equals t squared minus 3t, where s is the position and t is time. We can use Leibniz notation to show the process of taking the derivative, right? I could take the derivative of this. This is a polynomial. It is smooth and continuous, so I'm not going to have any issues. And if I want to do that, I'm going to say, hey, take it all and put it in my differential operator. So I'm going to differentiate with respect to which variable looks like it's going to matter? T. So with respect to t. And that should give me the derivative of s with respect to t. Because s and t are not the same, I know I'm not trying to do any rules, right? I'm just saying, hey, I'm going to have ds dt. These are different variables. So this is how we write it, which looks like what I would expect to see, right? Because that looks like my delta s over delta t for a regular rate of change. Equals, well, now on this other side, I can use my power rule because these variables match up. Right? And if those variables are the same, that means it makes sense for me to try to take the derivative using the power rule. And so I will get 2t minus 3. So this is the derivative of position with respect to time. And we just said that if you take the derivative of position, you're going to get to velocity. And actually, we should probably not have arrows this way. The arrows should go in one direction, right? So if you start with position, there, I bolded it a little bit more. So the fact that I just took the derivative of position means I have found my velocity function. Now, your task is to find the acceleration function. Okay, and we'll go over some more of these when we meet again in class. But thank you for being here, and I will see you next time. Bye.